In the name of God, the compassionate, the merciful, engineering plasticity, chapter 5, elastic plastic analysis of bending, part 11. In here, we have combined bending and tension. We had considered this combined bending and tension before, combined loadings, if you remember when we were talking about the yield point and the strain hardening and this kind of thing, but here we are looking at a bit difficult problem. Now this problem example is a disc. This is a disc and it has this kind of like a turbine blade. Okay, it's a blade, but it's not like a turbine blade, it's a simple blade. It's simple dimensions. The dimensions are like that. We are showing it from this section. So looking at it from here, this disc is like that, and this blade is like that. Okay, it's a kind of triangular blade looking at it from this side, this view. Okay. And we have given some dimensions here. The disc has a radius A and the blade has a thickness T. Okay, the thickness obviously changes in this view, but in that view it's constant. Okay, so we have here H0 and this H is varying along the blade. The length of the blade is L, and the disc and blade are connected here. So when the blade and the disc rotates with the velocity of omega, the blade also rotates with it. So we want to analyze this problem for elastic, plastic and completely plastic loading. In other words, what is the load here? The load here is the centrifugal force, because we have the weight of this disc and this blade, and they are rotating with the velocity, angular velocity omega. So if we increase omega, then the centrifugal load increases, and if the speed is high enough, the centrifugal force reaches the yield point and the material yields. So first we want to consider complete elastic loading before yielding. Now force on section H2. So because these sections are looking that way, the sections are changing, so we get a arbitrary section H2, which is situated from the center of the disc up to here somewhere is H2. Okay, so, and this distance is R. So we are saying that the normal force is rho H T S omega 2 ds. Let's have a look at this. Now, rho is the density obviously of this material. H for this section that we are considering. You see, we are considering the section H2. So the material in front of it is this material, is this triangular shaped material. Okay, that is the material in front of H2. We want to see what normal force is acting on H2. Okay, force on section H2. Section H2, of course, is a rectangular section, because if you look at this H2 from this view, the section is a rectangle H2 times T. Therefore, for the material in front of it, this rectangular shape geometry in front of H2, we have rho H, which is some arbitrary distance H, it could be anywhere in here, times T, So H times T is the cross section times S and times omega squared. Okay, what is this? This is mr omega squared. Remember the centrifugal force formula was mr. M is the mass, r is the distance, the radius, and omega squared, omega is angular velocity. Okay, so mr omega squared is this. Rho ht, okay, rho ht in fact is this, ht is this cross-sectional area in here, times rho gives us the, and r is s, okay, that is s, is r, and omega squared is angular velocity. And this ds, because we are taking a element, so that because this is a triangular shape, we take this element here and then integrate it between r, which is this distance, and b, which is this distance. So between r and b, between these two distances. And therefore ht times ds gives us the volume, okay, because it's an element, and times rho gives us the mass, and times omega squared and times s. Okay, so that is mr omega squared. Okay, that's how it is for h, and we have integrated it between r and b. Therefore we obtain the normal force for this H2. That's the normal force on H2. Now in here we have H over H0. H is this, H0 is this. Okay, these triangles, this triangle here and this triangle here. So H over H0 is B minus S over L. Okay, B minus S is this and L is this, these two triangles. So if we have this and substitute in here for H, then we get rho H0 times B minus S over L and times S omega squared ds. Okay, so that's what we have, because in here we don't have the H, so we can't integrate. So we substitute for H, and H surf B and S and L are known, so everything here is known, and variation is in S, and we have this integration here. So if I simplify this a bit, I get rho H0t omega squared over L bs minus S squared ds, and therefore I can integrate it between R and B, and this rho H sub t omega squared over L, everything is constant, comes out of the integration, and I integrate this bs squared over 2 minus s cube over 3. That is the limits of the integration. So I substitute these limits and I get this relationship, and I obtain N. Okay, so N is the force, normal force acting on any section H2. Okay, here you can see that if I change, let's see what are the constants. Rho is constant, H0 is constant, T is constant, omega here is constant, L is constant, B also is constant, B is constant. The only thing changing here is R. Okay, so if I put R in here, I get section H2. If I put R something like that, I get another section. So this formula or equation gives me the normal force at any section from here to there. Okay, for instance, this section I can put R equal to that value and get the normal force. Okay, so that's the normal force on any section of this blade. Right, let's have a look at and if you put R equal to A, you get interface of the disc and the blade, and that is where the maximum normal force for the disc is. Okay, now I have the normal force, so I can get the normal stress, sigma T we call it, okay, because it's a tensile stress. You know, the centrifugal force is acting on the section, so it is a tension force, a tensile stress, sigma T. So N divided by TH2, yeah, because that's the section H2 and that is the thickness. So TH2 is the cross section. So N divided by cross section gives me the stress. But because H2 is related to R, so I substitute for H2 what I had before, B minus R, H0 over L from these triangles. So sigma 2 becomes rho omega squared over 6 B times B plus R minus 2R squared. Therefore, I have the distribution of sigma T along this place on any section changing with R. So I can put R equal to A and obtain at the interface and put R any value and get the value of sigma T. Okay, now let's see what is the moment on H2 again. Now I have obtained the normal force in here, but I have a moment on H2 because this normal force which is acting on H2 is changing as we go along R. So it causes this blade to bend. So we have a moment on H2 and I obtained that one. So the moment also is rho HT S omega squared. That is what we had before times ds between R and B, and times H2 minus H. Because if you look at here, the element we took for obtaining the normal force was H here, distance S. Now if we look at this cross sections H and H2, then the difference between these two, just let me use my pen here if I can. Let me see if I can draw something simple here. Okay, so that bit, this H2 minus H gives me that section, and because the normal force is acting on the middle of the H2, therefore H2 minus H divided by 2 times the normal force gives me the moment. Okay, to explain further this relationship H2 minus H1 over 2y, this causes a moment. If we had this instead of this shape, which is a triangular shape, if we had a ordinary shape like this, the thickness was that and also the width was that. So we had a rectangular cross section and it is constant across this length L. If we had this, then any sections like H2, if you consider here or consider there or consider, the normal force acts in the middle and there is no difference between these sections, and therefore there is no moment. But here you can see we have the normal force in here on this section but in this section we have the normal force in here. So there is a difference as where the normal force is acting, and therefore there is a bending moment applied here due to the difference of the height of the sections in here and there. That's why we have written h2 minus h over 2. You can consider that the normal force here acts at the middle of h2, so, and here also at the middle of h, but h is smaller than h2. So the difference between h2 and h is what causes the bending moment. Now, here h2 minus h divided by s minus r equal to h2 divided by b minus r. And h0 divided by l, we get again this from these triangles. h2 minus h is this area, and s minus r, that is s minus r, is that length. So that length divided by that length is equal to h2 divided by b minus r. So that triangle, that big triangle, and this small triangle, that's what we have here, h2 divided by b minus r, and the other triangle is that one, which is h0 divided by l. So that triangle, this triangle, and this triangle, we have this relationship between them, and therefore we can write h is equal to h0 divided by l times b minus s, because we omit h2 from this relationship and then omit h in terms of h0 divided by l times b minus s, and substitute here for this, and we get this relationship. So in here we have substituted for h2 and h from these relationships, and we get this, we obtain this. Okay, again here what is varying and what is constant? Constants are rho, t, s, omega, h0, l. So we can take this out of the integration, and also here if we multiply these together we get bs squared minus bsr minus s cube r ds. So I can integrate that one, and if I integrate and substitute these limits, I will finally obtain such a relationship. So that is the bending moment. I have obtained the normal force, and the bending moment I have obtained the tensile stress due to the normal force. So I'm going to obtain the stress due to the bending moment, and here it is, sigma m max is equal to my over I max. That's for the bending moment, my over I. So if I put m here, y and I, and therefore I for the because h2 is a rectangular cross section, so I get th2 cube over 12, and for the rectangular cross section y is equal to h2 over 2. So in here y over I is this, so I substitute for sigma max in here, for m, y, and I in here. Also h2 over h0 is b minus r over l in these two triangles, this big triangle and the other one. h2 is the base here, h0 is the base. So these two triangles, we can write this relationship and use this relationship in this equation. We get sigma m max equal to rho omega squared b squared minus r squared over 4. Okay, this is simplified to this if we use this relationship, and obviously in here I have, in this equation I have put these, and also I have used this, so I can simplify this to this, and because here h is 0 is cancelled out, L squared is cancelled out, and etc, and b minus r squared also is cancelled out, so simplifies to this. This m I have put here for the bending moment, because the other stress that I obtained was sigma t for the normal force. This is the stress, the maximum stress for the bending moment, okay, due to bending moment. In here I'm going to obtain the maximum tensile stress, and where it happens. It happens at the bottommost fiber, okay? Bottommost fiber is this. That is the bottommost fiber at the bottom of the beam, okay? At the bottom of this blade, okay? Bottom of this blade is where the maximum tensile stress happens. Why? Because bending moment is on this small triangle, if you look at, trying to bend this outwards. Because if you consider the section H2, then this part of H2 is equal to H. So there is no bending moment of this on this section. The only bending moment is in here, is acting in here. So the material in front of this bit is acting to cause it to bend like that. So if it bends like that, goes like that, then the bottommost fiber is under tension. Also, we have tensile stress acting on H2 due to the normal stress. So we have the sum of these stresses at the bottommost fiber, okay? Because when we come to other fibers at H2, it is a maximum. The bottommost fiber is maximum, and it is tensile, as I explained, because this section, unsymmetrical part of this section, causes it to bend outwards like that. Therefore, sigma m, the maximum tensile stress, that sigma, is equal to sigma t, which was the stress due to the normal force and stress due to the bending moment. Add this together, we get the maximum tensile stress. Now, sigma t was this. I obtained this before, and sigma m max was this, as obtained before. So, sigma m then is the sum of these two, so I add them together and simplify them, and it becomes something like that. Rho is omega squared over 12, 5b2, 2br minus 7r2. Therefore, as this r is changing, you see, r is changing from r equal to a, r equal to b. So, putting r different values, we get sigma m. We want to know where it is maximum. So, I differentiate with respect to r and put it equal to 0, and if we do that, we obtain r equal to b over 7. Okay, b over 7. So if b over 7, at that position, maximum tensile stress happens. So I put this b over 7 for r in here and there, so we get sigma m max, and that is what we get in here. Sigma m is equal to 3 over 7 rho omega squared b squared. That is the maximum tensile stress at the bottommost fiber at this position, at r equal to b over 7. Because as you can see, this sigma m changes with r. So there is a maximum, and the maximum is that. Now, let's see. It says maximum stress for A equal smaller than B over 7. Now, if we have this disk and the radius of the disk is smaller than b over 7, because b is this total length. It includes L plus A. So if A is smaller than b over 7, then sigma m is this one, okay, because A is smaller than b over 7. But if A is bigger than b over 7, then maximum stress happens at r equal to A, because we don't have any b over 7, because the blade length is such that it doesn't happen at b over 7. So it happens at the interface, okay? So note that it's important, and that was the general relationship that we had. And so if we put r equal to A in this relationship, we get sigma m equal to that, and therefore that is the for this condition, for A greater than b over 7. For full elastic loading, the maximum elastic loading that we could get is the boundary between elastic and plastic. So we put sigma m equal to y. Okay, sigma m is equal to y. I put this sigma m equal to y, and I get omega squared from here. Omega squared is smaller or equal to 7 y over 3 rho b squared for A smaller than b over 7, and for A greater than b over 7, I get this. Okay, substitute for these in here, and you get these values. Okay, so for complete plastic loading, let's go to plastic. So far we considered the elastic loading and the boundary of elastic plastic, which is incipient yielding. Now we want to go to plastic loading. Obviously, if we look at this blade as a beam, then because it is bending like that, there is a positive stress and negative stress. But because this beam is unsymmetric, the neutral axis position is not known. Okay, it's not in the middle of the beam, because there is no middle. Where is the middle? So we don't know. So if we assume that the blade or this beam is completely plastic, we would have such a diagram on the section of the beam, okay, so that part of it is compressive and part of it is tensile, because it's doing like that, okay, and that is the neutral axis. So eta is the distance of neutral axis to this axis, and the middle line we have h over 2 and h over 2, okay, for a section like that. Therefore, the normal force is equal to minus y times h minus eta times t plus y eta t. In fact, this is the writing, because y is the stress, yield stress, times this area gives you the normal force, and that plus y times this area gives you the normal force. So that is the normal force. So if I write this, simplify it, I get that. So that's the normal force for completely plastic case. And the bending moment also, I can use this diagram like minus yh minus eta times t is this area, which is the normal force in here, and then times the distance, which is this h over 2 minus what? h minus eta, because h is the total, is total of that. So h minus eta is that bit, okay, but we are taking, because the force is acting in the middle, so we need half of this length. So that's why we have written h2 minus h eta over 2, okay, because h eta over 2 is half of that distance and h over 2 is half of that distance. So we get the bending moment for minus y. And for this plus y area also similarly, y times eta times t is the normal force acting in the middle, times h over 2 minus eta over 2. So that is the bending moment for this area as well. So that is m. And simplified, we get m equal to that. And if eta is equal to h, I mean if this was not a triangular shape and it was a rectangular shape, then eta would be equal to h, and n would be n0 t yh. And similarly, eta equal h over 2, m0 would be ty h square over 4. Now for this case, because eta is equal to h, we don't have any bending moments, okay, we don't have any bending moments. And for this case, eta is equal to h over 2, then we have bending moment m0, which is this, okay. So n0 means we don't have any bending moment, m0 means that we don't have a normal force. But here we have both of them for this case. And therefore, using this relationship n0, n0, n, and m, we could reach a relationship like that: n divided by n0 squared becomes that, and m over m0 becomes that. So that these two relationship we can have, and we can obtain eta from here and substitute it here, eta, obtain it from here and substitute it here, because eta is not known. And then we obtain this relationship, okay, this relationship, and if we simplify it, we get this relationship in terms of m over n0 and n over n0. We have a square power in there as well, and then simplifying it, we get this n over n0 squared. M over m0 is equal to 1. Okay, that is an interesting relationship. We call this inequality yield inequality. We call this yield inequality, and n over n0, we could put it that because we have obtained n before. Okay, we have obtained n before. If we consider this rigid plastic, then we could use this relationship, and we could also use this relationship as well because we obtained m before. This is for the rigid plastic, and therefore this inequality, using these relationships, can be used. And if we substitute for simplification, we do that. If I substitute for 1 minus rb as x, and for this value as p, then I get a simpler relationship like this: p squared x squared, and putting values for x, I can get values for p. It means that I can get a value for omega, okay, because p is omega, y is known, rho is known, b is known. So I can get a value for omega. For instance, here, if we put x equal to 0.82, then we get P equal to 0.59, and omega becomes like that for A smaller than B over 7. And also we have these relationships for the elastic angular velocity and completely plastic angular velocity. Okay, so you can see we can analyze any kind of problems, almost very difficult problem, this problem, but we used our analysis of bending and plastic moment to solve this kind of problem. And this yield inequality, if we plot m over m0 against n over n0, then these are the areas of interest. For instance, when m over m0 is 2/3 and n over n0 is 1, we are on the verge of the elastic plastic region. In here, any points in this green region is elastic, then any points in the blue region is elastic plastic, and this line here shows the fully plastic. So this elastic plastic means that part of it is elastic, part of it is plastic. That's the yielding, that's elastic plastic, and that's the fully plastic region. All of them, we have used this yield inequality in here to obtain this value. So this yield inequality could be of some use in other problems as well. In similar problems, you can obtain the yield inequality, and you can draw such a graph to see where are the points that you can load the geometry or what you have, whatever you have. What are the points that are elastic, what are the points that are elastic plastic, and at which point it yields, and at which points it becomes completely or fully plastic.